Math 265A, Cuesta College. I'm Joe Vasta, and we are going to do review 1. Let's go do some problems. We have a function. It is x plus 2 over 3x, and they ask us to find dq, which is the difference quotient. So that is what we're going to do here. And now with all these problems, I would highly encourage you to pause the video and see if you can do this on your own. Okay, so here it goes. dq is this right here, and I have some colors here. So what we want to do is we want to write this one right here, f of x plus h. So if I were to plug something into this function like 5, f of 5 is 5 plus 2 over 3 times 5. Now I'm not plugging 5 in, I'm plugging x plus h. So it's going to be x plus h plus 2 all over 3 times x plus h. So dq equals x plus h plus 2 all over 3 times x plus h. Okay, so there is the orange part. And that's not all of dq, because then we have a minus sign, and we have this f of x. So that's what I'm going to put next. So we have minus f of x, which is x plus 2 all over 3x, and then this is going to be all over h. Okay, so on the top, I'm not going to concentrate on the h right now, I'm just concentrating on the top. I'm going to get a common denominator, an LCD, least common denominator, a 3. It's going to have an x plus h, but it's also going to have an x. So this guy needs an x. And this guy over here needs an x plus h. And we're going to go ahead and put parentheses around the x plus 2. So let's go ahead and write our next step. I'm going to go x times these 3 terms. So this is going to be x squared plus hx plus 2x. Okay, so I did that, and then I have minus. I'm going to FOIL that out, and I'll keep it in parentheses. X squared plus hx plus 2x plus 2h. This is all over the LCD of 3x x plus h all over h, and then we'll put that h over 1. So it looks like I need another piece of paper here. So we'll continue. I'm going to do the copy dot flip right now. Copy the top fraction dot, because I'm dividing 2 fractions, and flip that. Now as I do the copy dot flip, I'll also distribute the negative sign. So this equals x squared plus hx plus 2x minus x squared minus hx minus 2x minus 2h. So this is all over 3x, x plus h. There's the copy, the dot, and then we flip the bottom, so 1 over h. Now on the top here, we end up getting a lot of things going away, like the x squared, negative x squared, and what else? The hx and the negative hx, and the 2x and the negative 2x. So on the top, we have just what? A negative 2h. And on the bottom we have 3. I'll throw the h in between the 3 and the x. So 3h x plus h. Okay, so I have one term on the top and one term on the bottom, which means I can cancel. I'll cancel the h's, and let's go ahead and continue this. I don't think there's much more we can do. Looks like I got -2 all over 3x x plus h. And there's the difference quotient. So that is some of the things we did. Now, in this review, I'm not going to review the diagnostic tests because we only have so much time. So I started with DQ. We'll do a modeling with functions, but before we do that, I think we'll jump a little into bug 6. This was the difference quotient. And notice with the question that we asked, it said x plus 2 over 3x. Well, in bug 6, I'll make the function be t plus 2 over 3t. And dq is the thing we just found. So where did that go? So it's right there. So all I did was copy it onto this piece of paper. And I'm going to put this in the context of the bug. We have a bug on the number line, and t is the input, which is time measured in seconds. And in this example, I'm going to say time is greater than 0 because we have a problem with the bottom of the fraction being 0. And the output, which sometimes we call s, but I'll say it's f of t. It's the position on the number line, and it's measured in feet. So in bug 6, they give you a function, and they ask you to find dq, which we did. And this one has t's instead of x's. And then another kind of question they would ask is, find the velocity function. Well, the velocity function, which looks like this, v of t, is really the limit as h approaches 0 of dq. And we kind of derived that in the earlier lectures. So we have the limit as h approaches 0 of dq, which is -2 all over 3t, t plus h. And this one, when I have a limit, I usually just put the number in and see if everything works out nicely, and this one does. So what my velocity function ends up being is -2 on the top and 3t squared on the bottom because h is 0. So my velocity function looks like this. V of t is -2 over 3t squared. And this describes my velocity, sometimes called the instantaneous velocity, of the bug at a particular time. So part B asks, what is the bug's velocity at 2 seconds? Well, what do you do with this 2? You plug it into the velocity function. So the hardest part about this problem is actually getting the dq. Okay, so v of 2 is -2 all over 3 times 2 squared. And you can actually figure that out. One of the 2's cancels, you get -1/6. Now, since we're talking, feet and seconds, we're going to say -1/6 feet per second. And that completes this problem. That looks like a problem from bug 6. Though in bug 6, I believe we didn't do rational functions, but this is something we should know how to do. Let's go ahead and do a modeling with functions problem. So you're definitely going to get a DQ on the exam, and you'll get something like this on the exam. You'll get a modeling with functions on the exam. This is going to help us with applications in calculus. So that's why we did this at the beginning. And you might want to pause the video and see if you can do this. The hypotenuse of a right triangle. So what I'm going to do is I'm going to draw a right triangle. Okay. The hypotenuse is that long side. It's the side that's across from the 90-degree angle, because it is a right triangle. It is twice as long as long. Okay, so we'll get rid of some of this. That's all right here. Okay, let's try this out again. The hypotenuse of a right triangle is twice as long as the long leg x. So we're going to call the long leg x. And it says the hypotenuse is twice as long as the long leg x. So I'm going to go 2 times x. Find a function that models its area a in terms of its long leg x. Okay, so first of all, we should label the short leg. We'll label it y. And they're trying to have us find this right here. Find a function that models its area in terms of its long leg. So we want a function that looks like this. This right here is our goal. Okay, do we know the area of a triangle? And the answer is hopefully yes. It is 1/2 base times height. So 1/2 x times y. Now, if this y wasn't here, we'd be able to say we're done because we have something called a of x. It's all in terms of x, but the y is there. So we need to cough up another equation that has a y in it, maybe an x, I don't know. And so when we look at this right triangle, maybe what we should think about is the Pythagorean Theorem. The one that goes x squared plus y squared equals 2x quantity squared. So that's what we're looking at. So let's go ahead and write this out. This is x squared plus y squared equals 4x squared. Okay, so what are we going to do with this? We are going to solve for something. Okay, so the letter that we want to get rid of happens to be y. So we'd like to get rid of that. So what am I going to do over here? I'm going to solve for y here. So this is what I want to solve for. Okay, so what I'm going to do is I'm going to subtract x squared on both sides. So 4x squared minus x squared is 3x squared. And then I'm going to take the square root property, which says y equals plus or minus the square root of 3x squared. Well, we know that y is a length, so it's not going to be negative. We also know that x is positive, so the square root of x squared when x is positive is just x. So y equals x root 3. So we have solved for y. We're going to put it back up into this area equation. The area equals 1/2 x times what y is, which is x root 3. So the area is, see on the top we have an x squared and a root 3, and on the bottom we have a 2. And if you want, it's optional, you can say a of x equals. Now, one other thing about this answer is that, let me write something down here. The thing about this answer is we like to put our coefficients in front of the x squared. So you might be wondering why I didn't with the square root. With square roots, lots of times I will put them at the end. because I don't want that square root sign to start going over the x squared. So you can write your answer like this. You just got to be careful to make sure everybody knows that the square root sign is not going over the x squared. I just prefer it this way. This is just a matter of style, but any other time I have a coefficient, like if it was x squared times 7, you would have to put the 7 in front just out of convention. People would look at you funny if that was a 7. Okay, well that completes this modeling with functions problem. Okay, so let's turn our attention to bug 1. So here's bug 1. What we did on bug 1 is we have a graph of a function here where the input is time, which is measured in seconds, that's the x-axis, and the output is position, which is feet from the origin, which is measured, in feet. It's from the origin on a number line. So the bug is walking on a number line. And what they want us to do in this problem is they want us to draw a diagram to represent the motion of the bug. And so let's go ahead and do that. I'm going to draw a number line. And we can see, here's time. At 0 seconds, the bug is at 5 on the number line. So let's go ahead and draw a number line. So at 0 seconds, the bug is right there. And then what happens as time goes on, as you go to 1 second, the bug is at 2. So it looks like the bug is traveling this way. And then at 2 seconds, the bug is at 1. And then look, it looks like this is where the bug turns around and then goes back to 2 at 3 seconds. So I'm going to make the bug go all the way to 1. And then I'm going to make him, so that's what he's doing. He goes all the way to 1, he turns around and goes right there. So you can see at 0 seconds he's at 5. T is 0. And at, let's just say at 2 seconds, this is where he came down and he dipped down at 1. So this right here is T equals 2. And then right here at 3 seconds, he's at 2 on the number line. So this is T equals 3. And that's the position of the bug. Now, I think I also did this problem another way. I said, okay, here's the number line right here, and I'll do it in red. And we can say, what happens? The bug starts right up here. He goes down, see, and then he goes up. He goes like that. Now, this can't be our final answer here. Whoops, and this is a little off. It should have gone down a little further. But then I was doing it like this and saying, okay, now let's just put this number line and flip it and make it that way. And so that's another way of looking at this problem. This right here happens to be the answer. Draw a diagram to represent the motion of the bug. And we better put a little arrow on the diagram there. So that is bug number 1. Bug number 2, I'm going to take this diagram. I'll draw it again on the next piece of paper. And we're going to ask some questions about this diagram. So there it is. There's the diagram. And they want to know the displacement. And these are time intervals from 0 to 3. So at 0 seconds, the bug is right there. And at 3 seconds, see it says T equals 3, the bug is right there. So the displacement would be 3 to the left, because notice, it looks like it goes 1, 2, 3. So 3 to the left, we're not going to write 3 to the left, we are going to write -3. -3 feet is the bug's displacement over that time interval. Now, is there a formula with function notation with end time and beginning time? Yeah, and we'll get into that. But for this, that's all we really need to do. The average velocity, not to be confused with the instantaneous velocity, which we did in the first problem or the second problem or whatever. Average velocity is over a time interval, and the instantaneous velocity is at a particular time. So what we're going to do is, average velocity is just the displacement over the time. Now the displacement is -3 feet. And the time within this time interval, well, that's not hard to see that it's going to be 3 seconds. And so our average velocity over that time interval is -1 foot per second. Now, is there a formula for this? Yeah. Is there a graphical meaning for this? Yeah, we'll get into that in the other bug handouts. Total distance traveled within the time interval from 0 to 3, so from here to here. Total distance traveled is you just track it on the number line. 1, 2, 3, 4, 5. I mean, that's the total distance that he traveled. So total distance traveled is 5 feet. Will always be a positive number for these problems. And so that is bug number 2. Okay, let's go ahead and do a problem from bug number 3. Time is seconds. S, or f of t, is feet. And I might give you a function here, and it looks like this. T squared minus 4t plus 5. Where is the bug at 5 seconds? Okay, so they're asking the position. They're asking us for the output, and they give us the input of 5 seconds. So this is what we do. We plug 5 into the position function, and it will tell us where. So let's see what happens when we do that. We have 5 squared, plugging it in here, minus 4 times 5 plus 5. So this is 25 minus 20 plus 5. And so it looks like we end up getting 10. We have to put the correct units, and they're asking us where. So at 5 seconds, the bug is at the 10-foot mark on the number line. Okay, and then now they ask us, when is the bug at 2 feet? So now they're asking for a time. They're asking for the input. They give us the output. So it might be easier for some of you to think of this function as s equals t squared minus 4t plus 5. This might remind you of when you had an f of x and you replaced the f of x with y. And they give us the s. So I'm going to put 2. I'll do my work over here. So I'm going to put 2 in for s. 2 equals t squared minus 4t plus 5. And now I have to solve this quadratic equation. So I'll subtract 2 on both sides. And then I'll try to factor this. Hopefully I will not have to do the quadratic formula here. This thing's going to factor into t minus 1, t minus 3. And so it says, when is the bug at 2 feet? Well, there's actually going to be 2 times. T equals 1, t equals 3. So at 1 second and at 3 seconds. Those are 2 times where the bug is at 2 feet with this position function. Okay, question number 3. What is the displacement from 0 to 3? Well, this is when we have to remember the formula. The formula says f of n time minus f of beginning time. So f of 3 is 9 minus 12 plus 5. Okay, so that's the first part. That's f of 3. And f of 0, well, that's pretty easy to do. It's just going to be 5. So looks like when you're done doing the arithmetic here, you end up getting negative 3. And since it's displacement, we're going to say negative 3 feet. Now, average velocity, we can put the displacement over the time, and that's great. We can figure that out really quickly, but I'm going to go ahead and show you the formula here. It's f of 3 minus f of 0. This is all over 3 minus 0. And so we've already done the one on the top. This is negative 3. And the one on the bottom is 3. This gives me negative 1 feet per second. So you might be wondering, wait a minute, Joe. Looks like we've seen these answers. And that is correct. We have seen the answers because this right here was exactly the same function that was used here. In fact, let's look at bug number 1, which was the same one. Here's bug number 1, and that's a parabola there. And in fact, when they said, when is the bug at 2 feet? Look, when is the bug at 2 feet? At 1 second and at 3 seconds. Look, that's when it has a s-coordinate, an s-coordinate of 2 at 1 and at 3. So what I did is I did this on purpose so you can see the different ways. Now on the exam, it might be a different, more complicated function, and if you just have a function without the picture, these formulas will always get you the correct answers. I'm not going to do total distance traveled with just a function without a picture, because we have to know how to find the minimums and the maximums. And we'll get into that later in this class. So that is the deal. Also, let me just point out one other thing. We said that the average velocity was negative 1. If you go and draw connect those 2 points, the one at t equals 0 and the one at t equals 3, you draw that secant line through the graph, it has the slope of negative 1, which is really the average velocity from 0 to 3. Okay, so that average velocity does have graphical meaning. So this takes care of bug 1, 2, and 3. Now look at with bug 3, I'm going to go to bug 4 and I'm actually going to use the same function. The same function is just the one we had there. This covers a little of 2.1 as well. And what they want you to do in bug 4 is fill in the table. Fill in the table for average velocity from 2 to 3, from 2.9 to 3, and 2.99 to 3. I've skipped the other one where I'm coming in from the right side, but this will probably be good enough for some of you. So if we get something like this on the exam, will we be able to do it? That is the question. And how would we do a problem like this? Well, with any of these threes, I'm just going to show you the work on one of these, and then you just go ahead and do the same kind of work, and you would actually use your calculator for probably, the last two. But the average velocity in the time interval 2 to 3 is f of 3 minus f of 2 all over 3 minus 2. Now, like for the next one, instead of putting 2 in there, you'd put 2.9 there and 2.9 there. And then you would do that in your calculator. So f of 3, we already did that. I believe that ended up being 2. Because you have 9 minus 12. So that's negative 3 plus 5 is 2. And then f of 2 is 4 minus 8. So we're at -4, -4 plus 5 is 1. And then 3 minus 2 is 1. So it looks like the answer for this part is going to be 1. So this is 1 foot per second. Which also describes the slope of the secant line, which connects t equals 2 on the graph to t equals 3. Now I'm just going to fill in the rest. You could pause this video and see if you can get these answers on your calculator. So when I got 2.9 to 3, I put that in my calculator. I got 1.9 foot per second. And then when I plugged this into my calculator, 2.99, you know, right there and right there, I ended up getting 1.99 feet per second. So here's the answer to this problem here, where I smeared that a little. And then they ask, what is the bug's instantaneous? So that could be, that's optional to put that. What is the bug's velocity at 3 seconds? So look, we're getting closer and closer to 3. You know, 2.999 would probably be 1.999. And so what is this number getting closer and closer to? Well, it's getting closer and closer to 2 feet per second. So there's the, that's our guess. 2 feet per second is the velocity at 3 seconds. Now, of course, we know that we can do a dq on this and take the limit as h goes to 0 and then get a velocity function and plug 3 into that velocity function. It should spit out a2. Okay, we've already done that in an earlier problem. What we want to do now is draw a line that is related to the instantaneous velocity at 3 seconds. So it says see next page, and I've already drawn this parabola, so I'll draw a lot nicer. So we're supposed to draw a line that represents the instantaneous velocity at 3 seconds. So we're going to draw a line that is tangent, that just kisses that graph at that point. And it should, we already know this because we kind of made our guess, it should have a slope of 2. And so this line is the tangent line, or is a tangent line at t equals 3. The slope is 2. You can check that out. Rise over run is 2, which also represents the velocity. And when we say velocity without anything in front of it, it means instantaneous velocity. Okay, so that is kind of the things that you do in bug 4. Bug 5. I'm going to give you the same graph, but now I use a different point. So here's a different point right here. This is the point at 4, this point is 4, 5. And it says use the point to find the bug's position, time, velocity. And I think I switched them around accidentally, but let's just look at this point here. So use this point 4, 5. So a point on this position function, the input is the time. So the time is 4 seconds. The output is the position on the number line. So the position is 5 feet on the number line. The velocity, now this is instantaneous velocity at that time, 4 seconds, would be the slope of that line there. So I'm going to go ahead and travel along the line here until I get to a nice point right here that comes right at the intersection of those two grids there. And then I'm going to be a little bug that is going to go rise over run. Rise is 1, 2, 3, 4 over run 1. So 4 over 1 is the slope of that line. So that would also tell you the velocity, 4 feet per second. Now, it's a coincidence that the time is 4 and the velocity is 4. That doesn't always happen. You could look at the last time of 3. But there it is. That is how you do the problems in Bug 5. Okay, let's go ahead and do some other kinds of problems. This is going to cover things from 2.2, 2.4, 2.5, and 2.6. We have a function, f, and we have lots of problems to do. So here are some of the problems where we analyze at each of these points. Here's x equals 7. We want the left-hand limit, the right-hand limit, and the limit. And then same with all these ones. So let's analyze 7 and see what happens. Okay, so we'll put, I'll circle these in orange. And then we're going to go to the graph at 7, which I'll highlight in orange. And we're going to analyze this. Okay, so the first thing they want to know, actually we can fold this piece of paper here. We'll go like this. The first thing they want to know is, what is f of 7? Now maybe you want to stop the video and see if you can do this on your own. So f of 7, well, there's the point on the graph, and that point is 7, 1. So f of 7 is 1. Okay, now if you're a little bug walking on this graph towards 7 from the left, before you step on 7, what is your y value coming closer and closer to? Well, it's coming closer and closer to 1. And as you are a little bug walking on this graph and you are to the right of 7, and you're getting closer and closer to 7, right before you step on x equals 7, what is the y value you're getting closer to? Well, it's 1 as well. Now we could say, look at this, the left-hand limit equals the right-hand limit, and so the limit as you approach from both sides happens to be 1 as well. The other way is, you say, are those two bugs going to meet? And yes, they are, and they're going to meet at the y value of 1. So that analyzes the point 7. I believe our next one, let me go ahead and fold this paper a little bit differently here. I wasn't really sure exactly how I was going to do this problem, but now I guess with folding the paper it works out hopefully pretty good. This one right here, which we'll do in yellow. Okay, and what is this one? So I want you to see if you can do this one on your own. F of 3 and the left-hand limit, the right-hand limit, and the regular limit, all at 3. That's right here. So see if you can get some answers on that one there. So f of 3, we go to 3 on the x-axis and we look up and down and see if we see the function. And we do, we see a point right there. And the y value of that point is 4. The limit as the bug approaches 3 from the left. Okay, so as I'm approaching 3 from the left, yes, there's a hole there and there's a dot up there, but I don't care what happens at 3. I'm about to step on what y value? I'm about to step on the y value, -1. So this one is -1. Hopefully this is all coming out on the camera. I'm not a professional cameraman, but when they told us to take our classes online, I suppose I had to do something. Okay, limit as you approach 3 from the right. As I am walking, I'm a little bug walking from the right-hand side. Right before I step in that hole, what's the y value I'm about to step on? Well, -1 as well. Left-hand limit equals right-hand limit, therefore, the limit's going to be -1. Another way of looking at it is those two bugs, as they approach 3 from both sides, they are about to step on the same y value of -1. I know there's a hole there and they're probably going to die, but who cares what happens at the point? Limits don't. Let's go ahead and take a look at the next x value. The next x value, this piece of paper is really getting folded, is the x value of 2. Okay, so yeah, this is starting to look really bad, but oh well, what are you going to do? So here's 2, which I kind of highlight in green. It says, what is f of 2? Well, f of 2 is, you look and you see the graph right there, you see a point right there, and the y value is -2. Okay, now what you're doing is you're taking the limit as you approach 2 from the left. As you are walking along this graph and you're to the left of 2, where are you about to step? Right before you step in that hole, you're about to step at the what y value? The y value of 1. Now, as you are approaching 2 from the right-hand side, well, who cares about this hole? You're right here. You're approaching 2 from the right-hand side. Right before you step on x equals 2, what are you about to step on in terms of the y value? Well, y equals -2. Left-hand limit and right-hand limit are different, aren't they? So what does that tell you about the regular limit? That tells you that that does not exist. D and E. And you can also see that the bugs, as they're traveling, right before they're about to step at x equals 2, they are not going to meet. So the limit doesn't exist. Okay, so this paper is getting pretty messed up here. So we need one more color. I think I'll use red on this. I don't want to use too dark of a color because then we might not see the number. We are going to be analyzing the graph, come on, at 5. And I want to make sure it's all in camera range. It is. And so I'm using red here. I'm going to put a, I'm going to color that 5 in red. And I want to ask, well, what is f of 5? Well, there's a vertical asymptote there, so f of 5 does not exist. D and E. Okay, now, as you're approaching 5 from the left-hand side, you're a little bug, you're walking along this graph. Where is your y value? Well, you're not going to be going toward one particular y value, but you are going, in terms of y values, to infinity. So this equals infinity. And we talked about infinity's a certain kind of, a special kind of D and E, but we have to put infinity. Now, as you're approaching 5 from the right-hand side, where is this little bug going? Well, this little bug is going down, not to a particular y value, but he's heading off toward negative infinity. Okay, so then they say, what is the limit as x approaches 5 from both sides? Well, the left-hand limit and the right-hand limit are not the same symbol. So we are going to say for this one, D and E does not exist. And this covers lots of limit problems. We've covered more than one section in terms of pictures, and that's pretty much what we've been filling out. We're going to fill out another piece of paper that involves this graph. So let me move my pins here. Okay, I don't think we need colors on this one, but you never know. What is the limit of f as x approaches infinity? Okay, so as x approaches infinity, which y value are you going to? Well, it looks like it's just going up, which means in terms of y values, you are going to infinity. So this equals infinity. What is the limit of f as x approaches negative infinity? Well, now you're kind of going off this way and you're going to negative infinity, and are you getting closer and closer to a y value? And the answer is yes, because there is a horizontal asymptote there, and the y value you are getting closer and closer to happens to be y equals 2. So the limit of f as x approaches negative infinity is it's positive 2. Okay, so I'll put the 2 right there. Find the values of x at which f is not continuous. Okay, so we want our points of discontinuity, and then they ask why, and that can come from the checklist. Okay, our points of discontinuity are the points where you would have to lift the pencil up to continue drawing the graph. So our points of discontinuity would be at 2. Where else do you have to lift the pencil up? 3 and 5. Okay, so I'm going to put those down. 2, 3, 5. Now, why is the graph discontinuous at 2? Does f of 2 exist? And the answer is yes. Does the limit exist at 2? Now we can look back at the other sheet. You can see that we said the limit of f as x approaches 2 was DNE. The bugs are not going to meet. So the reason why the graph is discontinuous at 2 is because the limit as x approaches 2 of our function does not exist. Okay, so here's the value of x, here's the reason why. Okay, what about 3? Why is it discontinuous at 3? Does f of 3 exist? Yes, it does. It's up here. Now, if that point wasn't up there and f of 3 did not exist, we would just say, okay, f of 3 DNE. But it does exist. Does the limit exist? And yes, you can look back. The limit as x approaches 3 is -1. So f of 3 exists, the limit exists. The problem is f of 3 does not equal the limit. And look, you can see it right here. F of 3 is 4. The limit is -1. So those do not equal. And so that is the reason for this one. So I'll say the limit, kind of run out of space here, as x approaches 3 of f of x does not equal f of 3. Okay, why is it discontinuous at 5? Well, the reason it's discontinuous at 5, let's check our conditions. Does f of 5 exist? And the answer is no, it doesn't. So we can stop right there and say, well, the reason is that f of 5 does not exist. So here's our answer for the points of discontinuity. Now they ask us something else. Find the intervals of continuity, and we are just going to list them, and we'll talk about why we don't use the unions when we're answering this question. You know, some of you were wondering, why don't we use the unions? The intervals of continuity would be, well, this thing is continuous all the way to negative infinity, so from negative infinity all the way to 2. So that's going to be our first one. Let me go ahead and go like that. So the first interval of continuity, and these are x values, negative infinity to 2. We put a parenthesis there because you've got to lift your pencil. There's nothing at 2 there. It's down there. Comma. The next interval of continuity happens to be from 2 to 3. Now here's the funny part, is we are going to put a bracket at 2 because it actually, you know, you can actually draw that point in right at 2 and start going without lifting your pencil. and you go to 3. With a parenthesis, because there's a circle there. You'd have to lift your pencil to actually fill that in. Now, I'm not done with this. I'm going to put another comma. The reason we don't put unions there is because if I put a union there, this would look like the interval of continuity. The first one would go from negative infinity to 3, and we know that there is a discontinuity at 2. So that's why we put a comma, because we're listing the intervals of continuity, and not a union, because then that would then simplify to negative infinity to 3. Our next interval of continuity would be, not including 3, 3 to 5, and not including 5. And then our next interval of continuity would go from 5 all the way, and we're looking at x values, 5 not including 5, to infinity. And so when they ask you to find the intervals of continuity, I mean, this is something you did in your homework, and this is just a review problem. We have covered 2, 2, 2, 4, 2, 5, 2, 6. I'm not saying we covered those all the way. There's other things in that, but in terms of the pictures, we did. So let's go ahead, cover some more problems here. We'll cover some stuff in 2.3. I want you to go ahead and pause the video and see if you can crank out these limits. Okay, so hopefully you got the answer. The limit as t approaches negative 2, so I'm going to just plug negative 2 in there and hope nothing bad happens. I get negative 2 squared plus 5 times negative 2 plus 7. So this is 4 minus 10 plus 7. And so what am I getting for this? I am getting negative 10. I have an 11 minus 10. This gives me 1. So the limit for this guy is 1. Now, I just pulled these problems right from 2.3. I didn't assign the evens, these even ones at least. And so hopefully, you know, these are new problems to you. So what is the limit as h approaches 0 of this creature right here? Well, we just put 0 in for h. So this is just going to be the square root of 16. And then we have plus 4 over there. So this is 3 over 4 plus 4. This gives me 3/8. So some of these limit problems are pretty quick, and that's good. Let's go ahead and do another problem from 2.3. Actually, I went ahead and grabbed this from the review exercises. This is number 16 from the review exercises. I figured I'd grab some evens because they don't give you the answers to those. Find the limit. Okay, well, let's see if we can. We put 4 in there. 4 times 4 is 16 times 4 is 64. 64 minus 4 squared is 16 times 7, so 16 times 7. Obviously, I don't have a calculator nearby. I should. Then we have a 48. This is all over 4 minus 4. Okay, that's a bad thing. On the top, we end up getting 8, 9, 10, 11. Well, carry that. Oh, on the top, we get 0 as well. So we have 0 over 0. So that thing is bad when it's 0 over 0. But what we could do with this is maybe factor out the top and the bottom and see if anything cancels. So that's what I'm going to do. So this is the limit as x approaches 4. I'll factor an x out. So I have x squared minus 7x plus 12. This is all over 4 minus x. And then this equals the limit as x approaches 4 of x. And then this thing actually factors. Factors of 12 that add to 7 would be 3 and 4. So this is going to be x minus 3. X minus 4, and look what we have on the bottom. We have a 4 minus x. So basically what you can do is you can factor a negative out of the bottom. So maybe you have something like this, and then it's an x minus 4. You see that that is the same as the bottom, and I rearranged the terms. And I smeared it a little, just, I don't know. Just little special things like this in a video lecture that count, the smearing of the pen. What we're going to do is we're going to cancel those x minus 4s. And so that actually indicates that there was a hole in the graph at x equals 4, and then there was a y value on that. So limit as x approaches 4. There's a negative 1 on the bottom. I'm just going to put that negative 1 right in front of that x. So negative x minus 3. Okay, so that equals that. I'm going to go ahead and plug the 4 in, just like I did originally, and see what happens. I end up getting negative 4 times, and then we have 4 minus 3. So it looks like my final answer is going to be negative 4 for the limit. What this looks like in terms of the graph, you don't have to care, but there is a graph. I would say that that looks like a parabola, and the parabola has a hole at x equals 4. So the bugs are still going to meet, and their y value is going to be negative 4. Let's go ahead and do another problem from 2.3. Pause the video and see if you can do problem number 18. Okay, problem number 18, I'm going to go ahead and put 3 in there. And so what happens when I put 3 in there? I get 3 times 3 is 9. 9 plus 16 is 25. Square root of 25 is 5. 5 minus 5 is 0 on the top. And on the bottom I get 0. So this is bad. So what we want to do, I'm going to go ahead and take the algebra under here without writing the limit a lot of times, because this one usually upsets people. Is I see a radical on the top, and then it's like minus a 5. So I'm going to rationalize the numerator by multiplying by, sometimes this is called the conjugate, root 3x plus 16, and instead of putting a minus 5, I'm going to put a plus 5 there. And on the bottom, since this is a fraction, I have to do exactly the same thing on the bottom. And I'll put parentheses around that x minus 3. So what does this do? Well, the reason you multiply it by the conjugate is this is a FOIL. And the outside and the inside, you can write them out if you want, but they are going to go away. They're going to cancel. So really, you just have to do an FL on this one. Your first would be you multiply root 3x plus 16 times root 3x plus 16, which is just going to be a 3x plus 16. The inside and the outside will go away, and then you'll have a minus 25. That's called rationalizing the numerator. Meanwhile, on the bottom, yes, we could FOIL that out, but it's going to make a mess. So let's not FOIL it out and just write it like this. X minus 3 times this mess right here. Problems like this, it makes me realize why people would want to go into a non-technical degree. I mean, look, this is our life. Wow, this is pretty pathetic. Okay, 16 minus 25 is negative 9. So 3x minus 9 all over. Let's just be lazy and say bottom. And then I can factor a 3 out of the top. So this is 3. Then we have x minus 3. Now I am going to write out the bottom. You can understand why I just wrote bottom the other time, because look how long this is taking me. Okay, now look what we can do. And I lined them up so I can just get them in one slash. Watch, I'll take out the thicker red pen just for your amusement. Okay. Okay, so those guys are gone. So what happened is this graph did have a hole in it, and we canceled. That when you cancel it, it tells you the graph had a hole in it. So this problem right here, wrong color, this equals the limit as x approaches 3, and then of this simplified expression here, 3x. I'm going to have like nightmares about writing out this denominator tonight. Great. Okay, so now I'm going to go ahead and put 3 into this and see if we can get some sort of limit. So I have 3 on the top, and on the bottom I have 3 times 3 is 9. 9 plus 16 is 25. Square root of 25 is 5. 5 plus 5 is 10. So I did a lot of the arithmetic. I just talked it out. That is how you do problem number 18. That was one where you have a radical and you have to do something by rationalizing the numerator, like we did here, and some of the problems you rationalize the denominator. Let's go ahead and do another problem. Another one from 2.3, and then we'll move on to 2.4. Okay, let's do this problem. Problem number 20 from the review exercises of Chapter 2, but it covers 2.3. I'm going to go ahead and put 1/3 in for t. So I have 1/3 minus 1/3 on the top. And then on the bottom I have 3 times 1/3 is 1. 1 minus 1. 0. 0 squared is 0. So this gives us 0 over 0. So just like the last few problems, we're like, what do we do here? Here's one thing we can do. It's not going to be as much algebra as that last problem that we did. But what I'll do is I'll factor a 1/3 out of the top. And I know that sounds a little weird, but let's just see if we can do that. When I factor 1/3 out of the top, I'm going to have a minus 1 there. Okay, because 1/3 times a negative 1 is negative 1/3. What should I put here so I will just have a t? Well, not just a t, because that's 1/3 t then. So maybe if you put a 3 in front of there, you end up having, oh look, that gives me the t. And look at the bottom. The bottom is 3t minus 1 squared. So you can cancel. This gives you the limit as t approaches 1/3. And those guys cancel. So you'll just have a 1/3 on the top, and on the bottom you have 3t minus 1, just one of those. Okay, now let's go ahead and put 1/3 into this problem here. And when you do, you end up getting 1/3 on the top and 1 minus 1, you get 0 on the bottom. Wow, that's crazy. So you have a number over 0. Now you're thinking, oh, well, Joe, that looks like it's going to be an infinity. Let's check it out a little more closely. Okay. If you took the limit, you have to investigate both sides. As t approaches 1/3 from the right of this function. You get 1/3 on the top. This pen is running out. Sure hope I have another one here. Oh, good. You get 1/3 on the top. I think I just made a mark on the wall. Okay. And then look, you get 1/3 times 3 minus 1. Now this 1/3 times 3, it's going to be a little bit more than 1/3. So that number there, it's not going to be 1. It's going to be a little more than 1 minus 1. So it's going to be close to 0, but it's going to be a positive. Great, another pen that doesn't work. So I mean, it works, but I can see it running out. Good, I got another one right here. You get a number over a very small positive number, which is infinity. And I know what you're thinking. You're thinking, that's what I was going to say here, but you have to investigate both sides. So I'm now going to say t goes toward 1/3 from the left. So I have 1/3 all over, okay, 3t minus 1. And so on the top I have 1/3. Now on the bottom, I put 1/3 in there, but this is a little bit to the left of 1/3, so less than 1/3, which is going to be a number that's a little bit less than 1 minus 1, which is going to be a very small negative number. And small, when I say small, I mean in magnitude. So this is going to be like 1/3 over negative 0.000000001. And that's, when you put that in a calculator or whatever, you're going to see that that gives you a really big number. So this is going to negative infinity. So what does this tell us? This tells us that our limit, this limit up here, does not exist. It also tells you that I lied to you because I said 2.3 and I thought it was 2.3. But I believe this is 2.4. Okay, because we are looking at limits that involve the infinity. Let's go ahead and do another 2.4 problem. This is number 28 from 2.4. So go ahead and evaluate these 4 problems by pausing the video. Okay, so it looks like I'm taking the limit of this function. It's the same function. My guess is, and I'm going to go over here and do this to the right hand side, is that I'm going to see if any canceling happens. So the top, I'm going to factor out AT. So this is t squared minus 5t plus 6. This is all over, and then I can factor a t squared out. T squared, and then we have t squared minus 4. Okay, let's keep factoring. So on the top, I have factors of 6 that add up to 5 would be 3 and 2. So t minus 2, t minus 3. Meanwhile, on the bottom, I have a difference of squares. So this gives me t minus 2, t plus 2. When I cancel here, that tells me there's a hole in the graph at 2, t equals 2. There's also a hole in the graph at t equals 0. But when I'm analyzing limits of this function, I can analyze the limits of t minus 3 all over t plus 2. Okay, so let's see what happens here. So I'm analyzing this. I want to go from, I want to approach negative 2 from the right. Okay, so as you can see, it's negative 2. It's going to be a 0 on the bottom. So if I'm approaching negative 2 from the right, you can think of a number like, you know, if you like, something to the right of negative 2 on the number line is negative 1.999. And I'll write that there just so you can think of what to do. Now, I mean, we could look at these functions here, but I'm going to look at this one right here. So this is just a negative 2 pretty much. But this right here is going to be a very small positive number. You see, negative 1.999 plus 2 is a very small positive number. So this thing on the bottom is going to be a very small positive number. You're saying, well, what happened to the negative 2 here? Well, negative 2 times a very, 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 very small positive number is a very, very, very small positive. It's still going to be this. Now on the top, when I put negative 2 in, I get like a negative 5. So it looks like part A, and this is number 28 on 2.4. Make sure that I did this right. Okay, I'm just checking my... Oh, I didn't do this right, okay? So, because I did dismiss something, didn't I? I dismissed a negative 2 going down here. So let's just talk about that. So this is a negative 2 right here. So shouldn't have been so easy to dismiss that, because look, that's going to make a big difference. A negative 2 times that is going to be a very small negative number, small in magnitude. Well, the thing is, this is really, so you got a negative here and a negative here. Those negatives are going to go away. You have like 5 halves, and you could just put that on the top, over a very small positive number. So it was like reckless of me to go, oh yeah, and just ignore that extra t. Okay, so I admit that I was reckless. And so we have 5 halves over a very, very small positive number, which gives us infinity. I'll be a little less reckless on the next one. We're going to take the limit as t approaches negative 2 from the left-hand side. So we put negative 2 on the top. Let's go like this and put a line here. We get negative 5. So I'm putting it into this function right here. So I have negative 5. And then on the bottom, I'm putting negative 2 in. So I'm going to put a negative 2 right here. And then I'm going to have, think of a number like to the left of negative 2, which would be negative 2.10001. Okay. You put that right there in for t, you're going to get a very, very small, and I'm saying that magnitude-wise, negative number. So you're going to get 0 minus. So notice, look, a negative, a negative, a negative. There's 3 negatives there, which is going to end up giving you a negative, and you've got that very small magnitude on the bottom, and you could say that you've got like 5 halves on the top. So this is going to take you to an infinity, but because there's 3 negatives, it's going to be negative infinity. So we'll put another line right here. This one's going to be quick because it says, what is the limit of this function as t approaches negative 2 from both sides? Well, you've already done the right-hand side and the left-hand side, and they do not match. So we are going to say it does not exist. Now, the limit of this function as t approaches 2, we knew that it looks like there's a hole at 2, so we think that it's going to exist. We're going to put 2, not into this, because I think we'll get 0 over 0. We're going to put it in there. So let's do this. 2 minus 3 is negative 1. 2. And then in the parentheses we have 4. Okay, so this one's actually going to be a nice answer of negative 1/8. And that's how you do problem number 28 from 2.4. Let's go ahead and do another 2.4 before we get into 2.5. So this is coming from the review exercises on page 129, and it is the limit as u approaches 0 from the right of this right here. So look what happens. On the top you get 0 minus 1, which is negative 1. On the bottom, you get the sign of 0. Well, the sign of 0 is 0, and if you remember the sign graph, it looks like that, okay? So this is y equals sine u. So make sure you know that when I draw this, I'm only drawing this graph to kind of jog my memory on terms of like what is the sign u. So I don't have to take out a calculator and press some buttons. So look at this. The sign of 0 is 0, but the sign of like something a little bit to the right of 0 is a small positive number. So the question is, what is negative 1 over a very, very small positive number? That's going to give me negative infinity. So that's the limit. So this graph is going to look different, and who cares about this graph? They never asked us to graph this graph. We're just finding out the right-hand side limit as u approaches 0. Okay, so here are some problems from 2.5. I want you to pause the video and see if you can do these problems on your own. Okay, the first problem, we have the limit as x approaches negative infinity of this polynomial. Well, really all we have to do when we do limits like this is look at the leading term. The leading term of this polynomial It's the one with the highest power. So we really just have to go like this. Limit as x approaches negative infinity, and we talked about this in lecture, of 3x to the 7th. Okay, so that's what that equals. I don't need the parentheses there, but I was feeling a little insecure, so I put them there. Okay, now I put negative infinity in for x. Well, you see this negative, it's really negative 1 times infinity. Negative 1 to the 7th is really going to be a negative. So I could take that outside. So this is negative 3 times infinity to the 7th. Well, what's infinity to the 7th? Well, that's just infinity. And then infinity times, let me just write that down. Negative 3 times infinity. Negative 3 times infinity happens to be negative infinity. And there's your answer. Now, if you were checking out this polynomial as you were going to negative infinity, and if you were graphing it, as you are drawing it, if you're drawing it to the left, you would be going down. That's what this says. Let's take a look at this one. This one is not a polynomial. So we've got to be a little bit more careful on this because a polynomial just has positive exponents. Let's see what happens. The first thing that I would do is probably rewrite this. This is a negative exponent, so let's see, limit as x approaches, once again, a negative infinity of this. This is going to be 2 over x to the 8th, cross the line, change the sign for the exponent, and then we have plus 4x cubed. So when I put negative infinity in there, I get 2 over negative infinity to the 8th plus 4, and then we have infinity cubed. Let's talk about this one right here. Negative infinity to the 8th is going to be an infinity. 2 over infinity, that goes to 0. Meanwhile, over here we have infinity cubed is infinity. Infinity times 4 is infinity. My final answer. Oh, okay. Almost messed it up. I'm plugging negative infinity in. I just noticed this out of the corner of my eye. I went ahead and somehow I forgot that I was plugging negative infinity in. So that's a negative infinity. We'll just, okay. I don't know what to do here. So that's 0, and this is negative infinity cubed, which is actually negative infinity. Okay, because that's negative, 3 negatives make a negative. So this answer is going to be negative infinity. Okay, so I was getting a little sloppy, and hopefully you see that when I was plugging negative infinity in. I don't know. Maybe I was thinking of something else, or maybe not. Maybe I was just being stupid. I do not cut these parts out of the video because then if you just see your teacher being perfect because they edited the video, it's a little less human and it's intimidating. I loved it when I was in a math class and my professor, we're talking higher math, messed something up because, you know, I feel stupid every day I go to class and then they messed it up. You're like, oh, wait a minute, he's one of us. So I will not cut that part out of the video. Okay, 2.5. So 2.5, another question from 2.5. Go ahead and pause the video and see if you can do this. This is page 129, review exercises. Take this limit as x approaches infinity. Okay, so when you do that, you end up getting infinity over infinity. So that's a bad thing. So what I'm going to do is I'm going to do some algebra in between some lines here. So I'm going to write out my rational expression. And I'm going to multiply the top and the bottom. And I look at the greatest power on the bottom, which is fifth. So I'm going to multiply top and bottom by 1 over x to the fifth. 1 over x to the fifth. Okay, so when I do that, I end up getting 1 over x minus 1 over x to the 5th. That's on the top. And on the bottom, I'm going to get 1 plus 2 over x to the 5th. Okay, so this is the limit. I went ahead and put another line there because this was just me thinking this out. I suppose I didn't really have to do that. Limit as x approaches infinity of this. Well, look what's going to happen. 1 over infinity is what? 1 over infinity is 0. 1 over infinity. Infinity to the 5th is infinity. That's 0. 1 plus 2 over infinity, 0. So this kind of becomes 0 over 1, which is defined. It happens to be 0. And so there was another limit there that we've computed. Let's go ahead and do another one. So 2.5, we're taking problems from the review exercises, even ones. The limit as z goes to infinity of this creature right here. Let's go ahead and put infinity in there. We have e raised to the negative 2 times infinity plus 2 over infinity. Okay, I'm going to do cross the line, change the sign on this one because the exponent's negative. 1 over e raised to the 2 times infinity power, and then this is 2 over infinity. Okay, what do we have here? We have 2 times infinity is infinity. E to the infinity is infinity, so I have 1 over infinity plus 2 over infinity. Both of those guys, we could have said that earlier about the 2 over infinity, both of them go to 0. So the answer to problem number 40 is 0. Let's go ahead and do another one from 2.5. So this problem, number 46 in the review exercises, they want you to investigate the limits as r goes to negative infinity and as r goes to infinity and see what happens. So let's do that. So these are like 2 different problems here. So this is 1 over 2 plus e to the negative infinity. Okay, so what are we going to do about that? Well, let's take a look at that a little closer. 1 over 2. And then this is really 1 over e to the infinity. Well, what is e to the infinity? That is infinity. I'll write this out a little more. 2 plus 1 over infinity. But this 1 over infinity here, that actually goes to 0. Now that's not 0 completely on the bottom of that fraction, it's just that little part of it. So this is really 1 over 2 plus 0, which is 1/2. Meanwhile, on this one, let's see what happens when you put infinity for this guy here. This gives you 1 over 2 plus e to the infinity. Okay, e to the infinity is infinity. What's infinity plus 2? Infinity plus 2 is infinity. This is 1 over infinity, which gives you 0. So we're done with this problem, but here's a follow-up problem. If this problem said, okay, well, what are the horizontal asymptotes to this graph? Well, you find all the horizontal asymptotes by doing these 2 kinds of limits. Y equals 1/2 and y equals 0. Okay, so this is just a little, this is extra. It wasn't asked, but it was asked in some of the homework problems. Okay, I think we have a few more and then we'll be done with this review. This one I didn't put a section number on because it covers a lot of the sections. The battery on the camera is dying out, so hopefully it doesn't cut out on this problem. So this problem says, I want you to draw the graph that has these characteristics. What are the characteristics? Well, it says this. It says the limit of f as x approaches -2. So we're going to be interested in this one right here, -2. And I'll circle these ones because they're both that. As you approach -2 from the left, it's infinity, and as you approach -2 from the right, it's negative infinity, which would mean that at -2 there is a vertical asymptote. As you approach -2 from the left, it says it's infinity, so it's going to be going up there and coming down. And as you approach -2 from the right, it's negative infinity, so you're going to be looking like that. Okay, the next one is approaching 0. Let's put this one in green. As you approach 0, now this says from both sides, because, you know, I mean, that's what it says, x approaches 0. It's infinity, which means there is another vertical asymptote, x equals 0, and it's going to be looking like this. The graph's going to be running up there on both sides. Okay, so those are kind of like arrows. Okay, now we're investigating 3 from the left, 3 from the right, and 3. So we'll circle this in yellow. So there's no infinities here, so we know there's not going to be vertical asymptotes. It says, as you approach 3 from the left, it is 2. So here is 3. We'll color that in. From the left, it is 2. So we're going toward 2 from the left. As you approach 3 from the right, it is 4. So as you approach it from the right, it's 4. And f of 3 is 1. So f of 3. So I'm going to put a closed circle here because it says f of 3 is 1, and I'm going to put open circles right there at 3, 2, 3, 2, and 3, 4. Just put an open circle there. Okay, now I'm going to be approaching this and going like that. Okay. The next one says as x approaches negative infinity, the limit of that is 0. So as you approach negative infinity or positive infinity, if you end up getting a number, that indicates a horizontal asymptote. So I'm going to go ahead and put a horizontal asymptote, y equals 0, which I have to kind of go like this because it's the x-axis. You won't be able to see a dashed line if I do it really lightly. And as you're approaching negative infinity, so as you're approaching this way, you're getting closer to this. So I'll just put an arrow there. And as you are approaching positive infinity, so we'll just put that right there, I guess. Positive infinity, the limit is negative infinity, which means the graph's going to be going down there. So let's see if we can try to put this all together. I have this vertical asymptote. On the left, it's going to be going up, and I have this horizontal asymptote, so we'll just try to put it all together. There is not one unique graph for this. I mean, there's different ways we can do this, and we'll talk about that. I have an asymptote here and, you know, 2 vertical asymptotes, and it looks like it's going to go like this. So it's going to maybe go up like that, and then it's going to come down, and at 3 it's going to connect to that circle, and then over here it's going to go down, do something like that. Now, of course, this part could have been a straight line going down with slope of -1. So there is some wiggle room, but this is a possible answer for this problem here. And we've had problems like that throughout our homework. Okay, let's go on to our last problem that we're going to do, which is continuity. Is it, yeah, continuous and limits. So this covers a few sections. It covers a little 2.6, but also some of the other sections. And you're taking the limit as you approach a from the left, as you approach a from the right, as you approach a from both sides, which I just label as L, and then it asks, is it continuous at a? So our a values are going to change. Our first a value is a equals 0. Now notice this graph here, it looks like this. It says x squared plus x over x. If I could take the green pen and write that, maybe, I've got to find room to write that. I'll write it right down here. So that branch could look like this. Factor the x out of the top. The x's cancel and you have x plus 1. So this top part, so if x is 0 anyway, it's not even going on that top part, it's going right there. So this top part is really x plus 1 for all we're concerned, because when x is 0, it's actually going to be 3 anyway. So let's investigate what happens at 0. Okay, the left-hand limit, you put 0 into this branch here, you get 0 plus 1. The left-hand limit happens to be 1. The right-hand limit, so a little to the right of 0, 0, you know, when you put 0 into the function, it's 3, but we're not doing that. We're just looking at a little to the right of 0. Okay, so we're plugging 0 in, and you end up getting 0 plus 1, which is 1. So the left-hand limit and the right-hand limit, they equal, therefore the limit is 1. Now, the rationale behind this is because really you've got a graph, and at 0, not that we have to graph the graph, at 0 you've got the graph x plus 1, which looks like this. But there's a hole right there. I mean, so we can graph this to actually analyze this problem as well. And then where the hole is, at x equals 0, the graph is 3. So here's 1, here's 3. And so like if you're more of a visual person, you might go, oh, I see that the left-hand limit is 1, the right-hand limit is 1, and the limit is 1. Now, is it continuous at 0? Can you draw this without lifting your pencil? No, it's not continuous at 0. And the reason it's not, so the answer to this is no. The reason it's not continuous is because f of 0, which equals what? 3, does not equal, I'll just say the limit, which equals 1. Okay, let's continue on here. A equals 1, so we're looking at the value of 1, and that's the cutoff from this one, x plus 1, to this one, which is 2. So you could say that this guy right here is on the left of 1, and this one is on the right of 1. So when I go left-hand limit, I'm going to plug 1 into here. So 1 plus 1 is 2. Now if I plug 1 over here, now I'm not supposed to plug 1 there, you know, when I'm evaluating the function, but let's go ahead. That's how you do the left-hand limit. Now the right-hand limit, I'm going to plug 1 into this. This is just a constant 2. So I get 2. And look at the left-hand limit and the right-hand limit. They are both 2. Therefore, the regular limit is also 2. Now, is this function continuous at x equals 1 or at a equals 1? Well, we should evaluate the function at 1 as well, and when you evaluate the function at x equals 1, you end up getting f of 1 is also 2. So f of 1 is the limit at 1, so the answer to this one is yes. And now I'm wishing I hadn't put the green right below there. Okay, so it is continuous at 1. Let's look at the value 4. 4 is another one of those cutoff points where you go from a horizontal line 2 to this line, which is y equals 2x right at 4. So left-hand limit, This is the one on the left, and even though we're not supposed to plug 4 into this function, I'm going to do that. I plug 4 into this branch, I get 2. The right-hand limit, I'm going to put 4 into this function, and I end up getting 4 times 2, which is 8. So what does that tell us? That tells us the left-hand limit and the right-hand limit are not the same. That means there's a little jump in the graph, and the limit does not exist. Is the function continuous at 4? And the answer is no, there's a jump. And the rationale behind that is because the limit does not exist. A equals 10. Well, 10, if you were to just plug 10 into this function, it would apply down here. You would say like f of 10 is, it would be 2 times 10, which is 20. Okay, so the left-hand limit and the right-hand limit are just gotten by plugging 10 into this branch here. I mean, the left-hand limit is going to be 20, the right-hand limit is going to be 20, and the limit is going to be 20. Look, f of 10 is 20. So, is this continuous? Is the function continuous at a equals 10? And the answer is yes. Now, for all you picture people, and you're like, you have no problem graphing this, you could have graphed this and answered all these questions using the graph. Yes, because the limit equals f of 10. And so that happens to be the last problem. So study hard, and I'll see you in the next video.